Okay, at this point, we've reached our position where we're now going to talk about our third exam. So first up, first thing that we cover that will be on your third exam is improper integrals back in 8.9. And remember, there are two scenarios that we're dealing with here with improper integrals. There are integrals that are going to infinity. And we've actually gotten a little practice back with those again as we've been looking at our integral test here. So we've got a little bit of practice with those again. So remember the notation, integral 1 to infinity of f of x dx. All right. We'd look at the limit as b goes to infinity of limit as b goes to infinity of integral from 1 to b of f of x dx. So that one should be the kind of the more familiar because we've just been doing that again here as we're using the integral test to test convergence of series. And then the other group were integrals at a vertical asymptote, right? Integrals at a vertical asymptote. Right, that would be a situation like this, where we have a vertical asymptote at x equals d, and let's say that we're doing the integral from a to d of our function. Then remember the way we did that is we did the limit as b approaches d, this time from below, of the integral from a to b of f of x dx. Okay. So if you go back into 8.9, you can check out some examples, and we'll just take a quick peek at some that we looked at previously. Here is an example we did early on, where we looked at 1 over x squared. Right? And we were able to see as we go to infinity, that becomes 1 over b plus 1. And of course, as we go to infinity, 1 over b goes to 0, and so therefore this thing goes to 1. Of course, we also looked at 1 over x, solved it, of course it diverges. Some other examples here. E to the minus 2x. We're going to work out, eventually see that it went to 1/2. 1 over 1 plus x squared. We're able to look at that one. Actually, we're doing that one both ways, minus infinity to infinity. So we actually had two different integrals we had to look at, minus infinity to 0 and 0 to infinity. All right, and so we worked out first the antiderivative, and then we focused on those. We actually figured out that the area beneath 1 over 1 plus x squared, as we go from minus infinity to infinity, actually worked out to be pi. Okay. Of course, you can't do anything about things like sine or cosine on their own, so they're kind of a little out of luck. Then we also again looked at vertical asymptotes. For example, we looked at the integral from 0 to 1 of 1 over x squared. So for that one, the asymptote was at 0. So we put a variable in and talk about a limit. We're able to work that out. And when we tried to evaluate that, we got that it went to infinity, so it diverged. Okay. On the other hand, when we looked at something like 1 over square root of x, that actually converged as we went to 0. 1 over x, unfortunately, still diverged. Okay. So we went through some other examples, and again, you can kind of look over those as well. Okay. So with the improper integrals. Okay. We then next turned to 4.7 and 7.6. That's where we were talking about our indeterminate limits in L'Hopital's rule. So up first we had our, in 4.7 we dealt with 0 over 0 and infinity over infinity limits. And that's where we go in and we go directly to the hospital to L'Hopital's rule. All right, those are the ones where we can directly go into L'Hopital's rule. If we have an infinity over 0, 0 over 0, we can apply the derivative to both the numerator and denominator. And so we went through various examples there as well. Various examples. Okay. And so again, you can check through. Remember, we do have these odd ones with square roots over x that actually kind of cycle if we keep going. So we're not actually, actually this one worked out. I was thinking this didn't work out, but it did, because there were some examples. I think it was when we had something in front side like an x squared. I'm thinking of something else. My apologies there. Remember, if it's not 0 over 0, we don't use the hospital, right? We can just, so don't jump into that. You might run across something like that. So again, we went through again lots of different examples that we were able to see. Okay. And then we talked about our other indeterminate forms. The hardest of those are the infinity minus infinity, generally. With infinity minus infinity, what we try to do is either come up with some way to factor something out or find some way to combine stuff. Right. Those are definitely the hardest of the examples. And again, go back and check through the notes. You'll see some examples there. Within 0 times infinity limit, remember what we do is rewrite it as one of the two things up in the top over the reciprocal of the other. Right, so when you have that product there, one of them goes to the top, and it's 1 over the reciprocal. Right, that gets us to a 0, 0 limit, and then we can use the hospital. Then we can go to the hospital and give it the surgery that we need. And then remember the other three, 0 to the 0, 1 to the infinity, infinity to the 0. If we're dealing with any of those, what we do is we compute the limit of the ln of that stuff and find out what that is. Okay, either that stuff goes to infinity, that stuff goes to 0, that stuff goes to some number. All right, so if that's equal to, say, a, then the overall limit is equal to e to the a. Okay, so that's what we did with, again, 4.7, 7.6 with these limits going to infinity. Okay. We then turned to 10.2. And of course, some of these you've seen again because they keep coming up. We're looking at limit of terms of a sequence, or we're looking at the limit, with the divergence test to check, whether a series converges. So we've been kind of seeing those things come up again and again. Okay. And then in 10.2 is where we introduce sequences. So just like we did at 10.2, you'll be given some questions where you're asked to list out several terms of the sequence, and then talk about whether it converges. Okay, talk about whether it converges. Remember, initially, we asked the question of convergence. We asked the question of convergence. We asked the question of convergence in terms of making a guess, but later on in 10.2, we're able to talk about the overall convergence of a sequence. So remember, initially when we first started working with that, we were just kind of guessing, based on what it looks like, whether or not something was converging or not. What it looks like based on the information. But then later on, we were able to talk about full-blown convergence. We were able to talk about full-blown convergence by looking at the limit of the terms of the underlying function that defines the sequence. All right, so by looking at limits, we were able to talk about directly how something converges. And this was the example I meant earlier on that L'Hopital's rule kind of breaks down on. Right, when we try to apply L'Hopital's rule to this with the k and the k squared, then unfortunately L'Hopital's rule breaks down. Unfortunately, in a situation like that, that's where we actually had to multiply. Okay. So what you can expect is kind of a combination of those questions, where you're going to have some where you're asked to list the terms in the problem, but then also talk about whether it converges. Okay. And of course, we also in 10.2 is where we introduce the geometric sequence. Right? A sub n equals a times r to the n, or alternatively, a sub n equals a sub n minus 1 times r. Right? Depending on whether we do it recursively or with a formula. Right? So you saw the geometric sequence, and we talked a little bit about that again in 10.2. Okay, we looked at some examples of seeing whether or not it converged or diverged. And of course, remember that a geometric sequence will converge to 0 if the ratio is less than 1. Otherwise, it's going to diverge. If r equals 1, it does converge to a. But -1, it's alternating, so it won't. Of course, if it's positive, you're going to diverge to infinity. We saw that with the two examples here that we looked at with the sequence, where we had a ratio of 2/3. That would lead to e to the ln of 2/3. Ln of 2/3 is negative, so it's e to a negative power, so that's going to go to 0. But on the other hand, with ln of 4/3, which is positive, that's e to a positive power. As you go to infinity, the whole thing is going to infinity, so it diverges. Okay, and then that brought us to 10.3, where we introduced the idea of infinite series. So the first thing to remember there was when we introduced the idea of the geometric sum. We had a formula for the geometric sum. Right, that was the sum as k goes from 0 to n of a r to the k. Remember, that's the partial sum Sn plus 1. Right, Sn plus 1. Right, and that's just a times 1 minus r to the n plus 1 over 1 minus r. If you want it the Sn sum, then that sum would go to n minus 1. And then we talked about the geometric series, which is actually easier to convert or to compute, because that's the sum as k goes from 0 to infinity of a r to the k, which remember that is just equal to a over 1 minus r. Okay, so definitely expect some problems where you're going to be given some geometric series. Remember, geometric series will converge to this. Remember, if the absolute value of r is less than 1. Right? That's going to happen. The absolute value of r is less than 1. Also with geometric series, I'd expect some kind of question asking you to use geometric series as you're working with a repeating decimal. So definitely expect some examples with those. And then also we talked about telescoping series. Now, as far as questions to expect with telescoping series, I would expect ones more in line with the first two examples I did. That last one, unless it was already written in its expanded form for you to work with, I wouldn't give you that problem. I would not give you one where, on a test anyway, where you're going to have to, do partial fractions to expand it out first. That's just too hard. I could, of course, give you it like this, the rest of the problem, right, where it's pretty straightforward to work out, or like the other two examples that we did, with the telescoping series. Okay, and then after that we had 10-4, and in 10-4 we had two main things that we talked about, which is the divergence test, which basically says that if the limit of the underlying sequence doesn't go to 0, it diverges. If the underlying sequence goes to 0, the divergence test is inconclusive. And then we had the integral test. We then had the integral test, okay, which is what we have just been looking at, where we're testing the convergence of a sequence based on the integral of its underlying, testing the convergence of a series, not sequence, by looking at the integral of the underlying sequence. Okay? So that is your kind of quick overview there of your test. Just now coming up.